You may have noticed a problem with this format, and that is that no matter how we set the bits, the mantissa is always going to be 1 point something something, because remember that the significant digit, the 1, that's always assumed to be there no matter how we set the bits. The problem then is that we don't have any way of representing the value 0. The solution is to set aside a particular bit pattern to mean 0. That is, we break the normal rules and say, well, this bit pattern, it's not interpreted in the normal way, it just means 0. And in the IEEE standard, that pattern is any pattern where the exponent bits are all set to 0, then this value is 0. It doesn't matter what you put in the mantissa, and it doesn't matter what the bit sign is. Well, actually, the standard says that there is both a positive 0 and a negative 0 value, so technically, yes, it does matter what this is. So because this is the high bit here is set, this is negative 0, and if it were 0, then we would have positive 0. Notice what this means is that normally an exponent with all 0 bits set should be interpreted as the exponent negative 127, but in fact there is no negative 127 in the IEEE standard because it's set aside to mean a particular 0. It's set aside to indicate a special value. So you can't have an exponent of negative 127 in the standard. Now in fact there are a few other special values in the IEEE standard, and 2 of these are positive infinity and negative infinity. Infinity is indicated by all 1s in the exponent bits and then all 0s in the mantissa bits. Positive infinity starts with a 0 in the signed bit, and negative infinity has a 1 in the signed bit. Now there are 2 more special values, and they are called quiet not a number and signaling not a number. Some operations result in indeterminate values, and for those cases you would use the result would be quiet not a number. It's a special value to indicate an indeterminate value. Signaling not a number is what you would use as the result of an operation that was illegal, an operation that didn't really make any sense. The way you represent these values is that the exponent bits are all 1. The sign bit can be either 1 or 0, it doesn't matter in either case. And then this bit here, which is normally the first bit of the mantissa, that is used to indicate whether it's quiet not a number or signaling not a number. When the bit is on, then it's quiet not a number. When it is off, then it means it's a signaling not a number value. The remaining bits can be anything, except when you have signaling not a number, they can't all be 0. Otherwise, if they were all 0 here, this would be confused for infinity. So at least one of these bits should be a 1. So because we have these special values that are reserved, that means that we don't have use of the exponents negative 127 and positive 128. They are reserved. Therefore, the exponent range in IEEE 32-bit floating point format, it's negative 126 to positive 127.